The common drawing of an atom with electrons orbiting around a nucleus in a plane is misleading, since electron orbits are a lot more complicated than that. But what about when we zoom out to our model of the solar system? Are the planets really orbiting in clean circles, all aligned on a flat plane? Actually, yes, for the most part. Our solar system is an orderly place, with the planets and asteroid belt all orbiting in almost perfect circles in the same direction, in the same plane around the sun. With the exception of Venus and Uranus, they even rotate in the same direction. Even the far-out Kuiper Belt objects appear to line up with that same plane, if more donut than disc-shaped. So why do all the planets orbit in a disk? Welcome to Bad Astra. Astronauts! Welcome to our wacky science channel where we talk about space, physics, and combat science misinformation with more costume changes than math. I'm Astra. I have a BA in physics, a master's in mechanical engineering, and a habit of obsessively researching commenter questions. Eris, a chaotic witch and our writer, is responsible for a lot of our more high concept videos. My wife, Nova, is the smart one and is finishing up her PhD in astrophysics. She's not only the science consultant on our physics videos like this one, but designed our logo and is responsible for this. Thank you so much for watching our wacky science videos, and we'd really appreciate it if you like, subscribe, and leave a comment down below. I read them all and try to respond to most of them. If you really love our videos and want to support us paying for increasingly elaborate costumes, props, locations, and filming equipment, we have a Patreon where you can sign up to get early access to our videos, behind-the-scenes updates, blooper reels, and other fun perks. So let's dive into our solar system. Planetary orbits aren't actually circles, but ellipses. An ellipse is like a flattened circle with a radius around two central points instead of one. The relative distance between the 2 points is the eccentricity. Circles are just ellipses with an eccentricity of 0, since the center point can be thought of as 2 points with a distance between them of 0. The eccentricity of any complete orbit will be between 0, a perfect circle, and 1, a parabolic orbit where the object won't be coming back. Technically, you can have hyperbolic orbits with eccentricities greater than 1, but those are less orbits and more random passing interstellar object got close enough to the sun for its direction to change. But none of the 8 major planets are very eccentric. The most eccentric orbit is Mercury at 0.2, which is just barely noticeable. Mercury's orbit is also tidally locked, which is interesting because each full Mercury day is exactly 2 Mercury years long.
Astra, shut up about Mercury. I am so sick and tired about hearing the sorry excuse for a planet get brought up all the time. It's not just Astra, it is the witches on Instagram as well. Everyone's like, Mercury's in retrograde, and I'm like, no, it's not, it just looks like that.
Now, the flat disk also isn't perfect, but it's pretty darn close. All of the 8 major planets orbit within 10 degrees of the plane of Earth's orbit, with Mercury, again, being the furthest off at a 7-degree angle.
No, absolutely not. We are not doing this to my husband, okay? Pluto should be a planet, because the definition of a planet that the IAU made up to exclude Pluto makes no sense whatsoever. A planet has to be nearly round in shape, which this does. That's a dumb rule anyway, since like Haumea is shaped like an egg, and Haumea should also be considered a planet because it's in the Kuiper Belt with all these other objects that are big enough to count as planets. Size doesn't matter. It's the heart of the planet that counts. And then the second rule they have is that it must be orbiting around the sun. Hello? Exoplanets aren't planets then? This is just a linguistics nightmare. This is what happens when you let scientists make linguistic choices that are based off of politics and feelings, not actual science. And the last one that kicked my husband out of the solar system, you know what that one was? Has to clear the orbit. Now, all the scientists may want to say that, oh my God, Eris, it means gravitationally dominant bodies. It doesn't mean like anything. Well, guess what? They should have specified that in the actual decision. I don't care what the scientists understand it as. They wrote it and in a way that excludes not only Pluto, by the way, but every single planet in our solar system except Venus and that ugly little Mercury. We don't live on a planet according to the definition. It is absolute utter nonsense. It's hogwash. And so help me, I get sad when I think about Pluto because it is so far away and I can't cuddle it. So it still has a great impact on my day-to-day life. And this jerk thinks that he's the one that killed Pluto. Well, guess what? Pluto is the Roman god of the underworld and death. You can't kill Pluto. Pluto is death.
Dwarf planet Pluto is a notable exception of both the mostly circular and mostly coplanar orbit rules. Pluto orbits in a very eccentric elliptical orbit, getting much closer and further away from our star at different times. In fact, from 1979 to 1999, Pluto was actually closer to the Sun than Neptune.
Well, guess what? Neptune hasn't cleared Pluto out of its orbit, so Neptune's definitely not a planet. And like anything with a moon isn't a planet, and anything with asteroids in the orbit is not a planet. So like, why does Mercury, of all the planets, the ugliest, tiniest little like abomination?
Is this orderly configuration of planets just random chance? The majority of star systems are binary, and we orbit a lone star. So is our coplanar planetary alignment also unique? Are there usually planets orbiting stars at a bunch of different angles? Actually, no. This phenomenon of planetary disks appears to be universal. The exoplanet systems we've observed also appear to have planets all orbiting in an orderly, flat disk. Observations show rings and disks are common in astronomy. Neptune and Saturn's rings, coplanar planets, the thin disks of spiral galaxies, and the accretion disks around black holes. So why is that? Why do planets align in disks around stars? I haven't mentioned the sun yet in all of this, which is a bit weird since it's the central gravity well anchoring the entire solar system, is thicker than a sequoia, hotter than lava, and hasn't responded to any of my texts. You know, I'm starting to think Professor Weber gave me the wrong number. Anyways, it's interesting to note that the planets orbit and rotate in the same direction as the sun's rotation, and orbit on the plane that happens to be the sun's equator. I wonder if that's related. Stars are formed when a cloud of dust collapses, often triggered or accelerated by a shockwave through a nebula or gravitational shearing as the galaxy rotates. The important thing is that particles get sent into motion, and then gravity brings them all together. It's important that those particles aren't stationary when they begin to collapse, but moving. We know from physics that momentum is conserved, and just like a figure skater pulling her arms in, as the moving dust gets closer to the center of mass, it speeds up. So when a dust cloud collapses into a new star, the conservation of angular momentum amplifies any initial tiny spin of the cloud into a defined rotation. Slower moving or close-in dust is going to fall into the growing center of mass pretty immediately, since mutual gravitational attraction is the only relevant physics at play. What's left is the dust that's fast-moving and decently far from the center of mass. As the cloud spins faster and faster, the difference between the dust at the poles and equator becomes important. All of the dust is being pulled towards the center of mass, a growing sphere, and all of the dust is spinning or orbiting on average in the same direction as the equator. Dust orbiting around the equator experiences the inward pull of gravity, but that pull is balanced out by the dust's path of inertia, and the gravitational pull becomes centripetal force. This is the same reason planets orbit stars and don't just fall towards them. Some people like to think of this effect as an inward gravity being balanced by an outward centrifugal force, but I think that's confusing since there's nothing pulling outwards. What's really happening is that from the dust's perspective, the force of gravity keeps changing direction as the dust orbits the new star. The dust is in free fall towards the center of mass, but is moving so fast that by the time it would have fallen into the center, it's already on another side. In its frame of reference, the new star is moving around the dust, constantly pulling it in changing directions and keeping it stuck in a fixed position. Now that we've looked at the dust around the equator, let's look at the dust by the two poles. This dust is also spinning around a central point, but notice how as it orbits, the force of gravity is always pulling it in the same direction? There's no direction change to balance out the overall force on the dust. And when forces on an object are unbalanced, you get acceleration. Specifically in this case, downward acceleration into a newly forming star. The dust at any latitude where the pull of gravity is in the same direction, even in part, will slowly fall in. Eventually, only fast-moving dust at the equator is able to avoid getting swallowed by the young star. Thus, the dust spinning collapses into a disk, the only sustainable balance between gravitational collapse and quick orbital motion. Now, if an object passing by in a different direction got captured by the star's gravity and started orbiting around the poles, that could be a sustainable orbit. Orbits don't have to be in the same direction as a central body's rotation. It's just that as a dust cloud collapses into a star, all of that dust tends to be spinning in the same direction due to momentum conservation. Okay, skip ahead past nuclear fusion starting, and now we have a disk of gas orbiting a younger star. That dust will attract itself together. Collisions happen, and larger bodies form out of the dust over time. Asteroids, then planets, form slowly out of a disk of dust surrounding the new star. Because that dust disk was all in a plane, the planets form in that plane as well. The planets are an averaging of all the inertial of the dust that made them up, orbiting because the initial dust in the planetary disk was orbiting, and rotating due both to the initial spin of smaller objects and to collisions between bodies as the planets were forming. Most of the planets rotate in the same direction, with the exception of Uranus and Venus, likely due to later collisions changing their direction. So how do we know all of this? Well, theoretical astrophysicists figured it out, and observational astronomers have spotted protoplanetary disks at different stages of star and exoplanet formation. Thanks, Hubble! For the most part, we see star systems, singular and binary, at various stages of development forming in this way, ending up all on a plane. I say for the most part because there is a weird exception I read about. A 2019 paper details a binary star system where two stars orbit each other in one plane, like a carousel, and a planetary disk appears to orbit around them oriented over the plane of the star's poles, like a Ferris wheel surrounding that carousel. Oh, and to add complication, two more stars orbited outside of the planetary ring, making this actually a quaternary system, which is crazy rare on its own. Clearly, some weird physics is happening here. Let me know in the comments if you'd like me to do a video just deep diving into this wild system. For now, I've linked the sources I read in the description. We've learned that planets form very slowly from dust in planetary disks, But planetary disks don't last forever. Over time, stellar winds blow the gas and dust away. The bigger the star, the stronger its stellar winds. Blue supergiants, type O and B stars, give off such intense stellar winds that even stars nearby often have their planetary disks blown away before planets have time to form. The longer planetary disks last on average, the more systems have time to develop planets. And that affects whether we are alone in the universe. So, how long does the average planetary disk last? Astronomers estimate average disk lifetimes by observing a ton of star clusters of known ages and measuring the fraction of stars that still have disks at those different stages. Until recently, astronomers estimated that planetary disks lasted between 1 and 3 million years on average, which is a really short amount of time in astronomical timescales. But there was a weird problem with the results. The further away a star cluster was from Earth, regardless of its age, the fewer stars had disks and the shorter the estimated disk lifetime. Why was that? Let's talk about observational bias. Further away star clusters appear dimmer, so it's harder to see most stars. Astrophysicist Suzanne Falzner of Forschungszentrum Jülich in Germany explains that although lower mass or dwarf stars smaller than our sun constitute the vast majority of stars, they can be too dim to spot from far away. So if astronomers can only see larger stars, which have stronger stellar winds, that sampling bias will make the average planetary disk lifetime seem a lot shorter. With this sampling bias understood and accounted for, new estimates say that planetary disks probably last up to 6.5 million years on average, with some planetary disks lasting between 10 and 20 million years, which leaves a lot more time for planets to form.
Okay, I want to get back to dunking on Mercury. Why does Mercury get to be a planet? It's just so gross. Like, oh my god, look at the colorized infrared. It's blue and gold. That's so great. No, you know what's great? The infrared image of Pluto. That's so much prettier than Mercury. You can look at any of the other planets, all of them look better than Mercury. Venus is the hottest planet, while Mercury failed to do that, even though it has a distinct advantage over everybody else. Mediocre white man if I ever heard it.
So if there are flat planetary disks which form around stars, can't they also form around planets? Why, yes. In fact, Saturn and Neptune both have rings. Another fun fact, the Earth isn't actually a perfect sphere. No, the Earth is not flat. It is an almost perfect sphere, just like the planets orbit in almost perfect circles. Earth is actually an oblate spheroid, which is math for squished a little, bulging at the equator and compressed at the poles. The difference is measurable, with the equatorial diameter being 42 kilometers longer than the diameter between the poles. Since the total diameter at the equator is 12,756 kilometers, the poles are just under 1/3% closer together, which is a ratio just within the tolerance for regulation billiard balls. Whether or not the Earth is smoother than a pool ball actually depends on whether you use the official regulations, yes, or the current manufacturing standards, no. And it's actually pretty close either way. Okay, back to the solar system. If we didn't know about how the sun formed with a planetary disk, we would assume that the main planets, dwarf planets, and asteroids should all orbit at random orientations, since gravity acts equally in all directions. And beyond the Kuiper belt, the Oort cloud is hypothesized to be a sphere of far-out space debris. Now that we've officially gone off on at least 3 tangents past the flat Earth mentioned and reached the niche fun geophysics fact, I think it's time to wrap up this video. Leave a comment about billiards if you made it to the end, and remember that science is a process. Astra out.
Ad Astra, to the stars, to the stars.